Okay, this lecture is on linearization and differentials, and they're very closely related. So we'll start with single variable calculus. Here we have a function in blue, I think. And what we're going to do is pick a point, a number here, and we're going to estimate this function by constructing a linear equation, a line, that's tangent to the function at that point. And we say that the linear function is approximately equal to the actual function. In fact, they're the same at this point, but they're close, near to that point. So the goal here is to construct an equation for L. And I think you can see just by looking at it, L, an arbitrary value for L, is just this value plus this value. So let's write that down in red. L, as a function of the single variable x, is the value of the function at x naught plus, well, this rise is really the rise over the run times the run. So what's the rise over the run? Well, that's just the derivative at x naught, and the run is just x minus x naught. Okay? And that's all there is to it. Notice that this is a number, this is a number, this is a number, this is a number, this is a number. So what you're left with is the variable x. X could be anywhere along the red line. So it's a function in a single variable x that is necessarily linear. So now the next step is to say, well, what's the differential? Well, differential is really the same kind of thing, except we're going to let this arbitrary value of x slide down the red line to this point. So then the change in the function becomes instantaneously small, and the change in x becomes whatever the word is, very small. So how do we write that? Effectively, we're going to take this number, put it on the other side, and change the sign. So we have L minus F, but because we slid down the red line, that change is going to be the differential of the function f. And what's left on the right-hand side is the rate of change, and x naught could be anywhere. So it's the derivative at x times, well, this delta, this change of x, is now an instantaneous change in x, so it's a dx. This is a differential, this is a differential, this should look familiar. If we take this, put it over here, we say the derivative is df, or dy, divided by dx. Okay. So actually this should be in blue because this is true for all x. So now we'll go to multivariable calculus. It's almost the same thing. Now you have a function, f, and it's a surface. And it's in three-dimensional ambient space. Surface and space. Okay, we pick a point, much like we picked a point here. We're going to pick a point here, which has two components, x naught, y naught. So we go up, and here's the point on that surface in blue, and now we want to approximate it through a linear function in two variables this time. Well, that's a plane in red. Okay, so how do we do that? Well, we say that f of xy is approximately equal to L of xy, just like before, and we write L in red. We write L, the linearization, So what's it going to be equal to? Well, just like before, it's the value of the function at the point. So it's f of x naught y naught plus, now we need to add the rate of change times the change in x. Well, the rate, well, things are changing in the x direction and also in the y direction, in the x direction and the y direction. So we first must write the partial of f with respect to x at x naught, and the change of x is just like before, x minus x naught, plus, well, now we have, this is multivariable calculus, we have another component. We have the partial with respect to y at y naught times y minus y naught. And that's our approximation. That's our zooming in linearization of the function in blue by looking at the plane in space associated with that point. We say L is exactly equal to F at this point, and L is near F at points near this point in the plane, or actually this point in space. Okay, so now what's the differential? Well, again, we're going to take this, put it on the other side, and let arbitrary values of x, y get closer and closer to x naught, y naught. So when we do that, reasoning as before, I don't have room, so we'll just do it here, and this time we're going to use blue, whatever the color is, and we'll say the differential in multivariable calculus is equal to, well, it's the rate of change for a value of x, but it's the partial of f with respect to x, and the variable is x dx plus the partial of y, which is a function of y, dy. And this is a differential, this is a differential, this is a differential. So you can just look at it and say, hey, if we just get rid of this, this looks a heck of a lot like this. And it is. The only difference is it's not called the derivative of x, it's called the partial derivative of x, because it's got really two pieces. And that's all there is to it. Not that hard, is it? Thank you.